different. Uh, you know, have you ever thought about the word equal? It sounds simple. You might think it just means two things are the same. But in the worlds of math and computer science, same can mean different things. We often see the equals sign and think we know its whole story. But there is another symbol, congruent, that also talks about sameness. Understanding the difference between these two ideas is like getting a secret key. It unlocks a deeper understanding of how both mathematics and programming work. This is not just a picky detail, it is a fundamental concept that helps us stop guessing and start knowing. This essay is a journey. We will start by exploring that very difference between equality and equivalence. Think of it as our first step into a larger world of ideas. From there, we will look at the basic building blocks that mathematicians and programmers use every single day. We will talk about the different families or sets of numbers. Let's start with the most familiar idea, equality. When we use the equals sign equals, we are making a very strong and direct statement. We are saying the left side has the exact same value as the right side. It is a declaration of perfect balance. For instance, if we write 2 plus 3 equals 5, they are interchangeable. You could replace 2 plus 3 with 5 in any equation, and the meaning would not change. This is the kind of equality we learn first in school. It is concrete, absolute, and leaves no room for interpretation. Now, let's introduce a new player, equivalence. Equivalence is a more flexible, context-dependent idea of sameness. It is often shown with the symbol congruent. When two things are equivalent, they are the same in a specific way or by specific rules. They might not be the exact same number, but they share a crucial property within a system. Modular arithmetic is a great example. It is like clock math. On a 12-hour clock, 1 o'clock and 13 o'clock point to the same spot. So, 13 congruent 1 mod 12. They are equivalent in the context of a 12-hour cycle. So, what is the big takeaway here? Equality is strict. It is about identical value. Think of it as two identical twins who are impossible to tell apart because they are the same in every single way. Equivalence is about shared characteristics. Think of it as two people who are not identical but are both wearing the same red hat. They are not the same person, but they are equivalent in the category of people wearing red hats. This distinction is incredibly important. In programming, a single equals sign equals often means a sign of value, while a double equals sign equals equals is used to check for equality, asking, are these two values the same? Understanding both concepts allows us to be more precise. When we are doing simple arithmetic, we use equality. When we are working within specific systems like logic or number theory, equivalence becomes our tool. For example, in logic, we might say that two statements are logically equivalent if they always have the same true or false outcome, even if they are worded differently. The statement, if it is raining, then the ground is wet, is logically equivalent to, if the ground is not wet, then it is not raining. They are different sentences, but their logical meaning is the same. Recognizing this difference stops us from making wrong assumptions and helps us reason more clearly. Section 3. The building blocks of numbers. Sets and bases. All the math we do relies on different kinds of numbers. To keep them organized, mathematicians group them into sets. Think of these sets like nested boxes, with each box holding more types of numbers than the one inside it. The simplest set is the natural numbers, n, 0, 1, 2, 3, and so on. They are great for counting apples, but what if you owe someone an apple? For that, we need the next box. This is the set of integers, z, which includes all the natural numbers, their negative counterparts, and 0. But what about numbers between the whole numbers, like half a pizza? For this, we open the next box, the rational numbers, q. This set includes any number that can be written as a fraction, or two integers, 1/2 negative, 7 quarters, 5, 5 over 1. If you can write a number as a decimal that either stops, like 0.5, or repeats a pattern forever, like 0.3 repeating, it is a rational number. Still, there are gaps on the number line. Numbers like pi, or the square root of 2, have decimal forms that go on forever without repeating. These are called irrational numbers. When we combine all the rational and irrational numbers, we get the real numbers. R. This set represents every single point on an infinitely long number line. For most of the math we do in everyday life, this is as far as we need to go. But there is one more, even bigger box, The complex numbers, C. These numbers were invented to solve equations like x squared equals -1. They take the form a plus bi, where I is the imaginary unit, defined as the square root of -1. This set includes all the real numbers plus a whole new dimension of imaginary numbers, opening up incredible new areas of mathematics and engineering. Just as important as the type of number is how we write it down. We typically use the base 10 or decimal system. This means we have 10 digits, 0 through 9, and the position of a digit tells us its value in powers of 10. The number 253 is really 2 times 10 squared plus 5 times 10 to the 1 plus 3 times 10 to the 0. Computers, however, think differently. They work with electricity that is either on or off, so they use the base 2 or binary system. Binary only has 2 digits, 0 and 1. The binary number 101 means 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0, which is 4 plus 0 plus 1, or 5 in our decimal system. Programmers also use base 16 or hexadecimal shorthand for long binary numbers, using digits 0 through 9 and letters A through F. We have seen that computers think in binary, using only ones and zeros. This is perfectly fine for whole numbers, the integers. We can represent any integer perfectly in binary, just as we can in decimal. The number 25 can be written precisely, with no ambiguity. However, things get a bit messy when we move from integers to numbers with decimal points, which programmers call floating point numbers. The problem is that the way we represent fractions in base 10 does not always translate perfectly into base 2. This mismatch is the source of a common and sometimes confusing issue: floating point rounding errors. Consider the simple decimal fraction 0.1 or 1/10. In base 10, it is clean and finite. But when a computer tries to store 0.1 in binary, it runs into a problem. The fraction 1 over 10 in base 2 becomes an infinitely repeating sequence, 0.00011001100011 and so on. It is similar to how the fraction 1/3 becomes the repeating decimal 0.333 in our base 10 system. Since a computer only has a finite amount of memory to store a number, it has to cut off that infinite sequence at some point. This means the number it stores is not exactly 0.1, but a very, very close approximation of it. This tiny imprecision can lead to some surprising results. For example, if you are using a programming language like Python, and you ask the computer to calculate 0.1 0.2, you might expect the answer to be exactly 0.3. However, because both 0.1 and 0.2 are stored as approximations, when the computer adds them, the result is an approximation of 0.3. The actual number stored might be something incredibly close, like 0.3004. For most practical purposes, this difference is so small that it does not matter. But if you write a program that directly checks if 0.1 plus 0.2 are on 0.3, the computer will say, false. This is not a bug in the computer or the programming language. It is a fundamental consequence of representing fractional numbers in a fixed size, binary format. It is known as a floating point rounding error. Programmers learn to work around this. Instead of checking for exact equality between two floating point numbers, they check if the numbers are, close enough to each other. For instance, they might check if the absolute difference between the two numbers is smaller than a very tiny tolerance level. Understanding this concept is crucial for writing robust code that deals with non-integer measurements and calculations. It stops you from guessing why your flawless logic is producing unexpected results. Beyond numbers, mathematics gives us a powerful system for thinking clearly. This system is called logic. At its core, logic deals with propositions, which are statements that can be definitively true or false. For example, the sky is blue is a proposition. What time is it is not, because it is a question. Logic provides us with operators to combine these simple propositions into more complex statements. The three most basic operators are and or not. The AND operator is true only if both propositions it connects are true. The OR operator is true if at least one of the propositions is true. The NOT operator simply flips the truth value of a proposition. To see how these operators work in every possible scenario, we use something called a truth table. A truth table is a simple chart that lists all the possible combinations of true and false values for our propositions and shows the resulting truth value. For example, for two propositions P and Q, the statement P and Q is only true when P is true and Q is true. In all other cases, if P is false, or Q is false, or both are false, the statement P and Q is false. These tables are an essential tool for verifying logical arguments and are the basis for how computer circuits are designed. When we build these complex logical statements, they fall into one of three categories based on their truth values. Tautology. A tautology is a statement that is always true, no matter the truth values of its individual parts. A classic example is the statement P or not P. Think about it. Either a statement is true or it is false. So one of those two options must be true, making the combined OR statement always true. For example, it is either raining or it is not raining. This statement is true no matter what the weather is actually doing. Contradiction. A contradiction is a statement that is always false. The most famous example is P and not P. It is impossible for a statement to be both true and false at the same time. You cannot say it is raining and it is not raining and have that be a true statement. Contingency. If a statement can be either true or false depending on its parts, it is a contingency. Most logical statements we encounter are contingencies. For example, the sun is out, and I am happy could be true or false, depending on the weather and my mood. Now let us explore a fascinating branch of math number theory which studies the properties of integers. A central concept here is modular arithmetic. The expression A is congruent to B mod M means they have the same remainder when divided by. For example, 17 divided by 12 is 1 with remainder 5. 5 divided by 12 is 0 with remainder 5. Since both have remainder 5, 17 is congruent to 5 mod 12. This clock arithmetic is incredibly useful in computer science. Cryptography generating patterns. Within the integers, a special set of numbers holds immense importance, the prime numbers. A prime number is a natural number greater than 1 with no positive divisors other than 1 and itself. 2. 3, 5, 7, 11, 13, 12 is not prime because it can be divided by 2, 3, 4, and 6. The fundamental theorem of arithmetic says any integer greater than 1 is prime or a unique product of primes. This is prime factorization. 60 equals 2 times, 3 times 5. A common task is finding the greatest common divisor, the largest number dividing both. Instead of listing factors, use the Euclidean algorithm. Show flowchart of Euclidean algorithm for 48 and 18. It works in remainders. Step 48 divided by 18 equals 2, remainder 12. Step 18 divided by 12 equals 1, remainder 6. Step 12 divided by 6 equals 2, remainder 0. Last non-zero remainder equals 6, so the GCD is 6. These ideas lead to powerful theorems. One of the most famous is Fermat's Little theorem. If P is prime and A is not a multiple of P, A to the power, P minus 1, is congruent to 1 mod P. For example, P equals 7, A equals 3. 3 to the 6th is 729. 729 divided by 7 is 104 with remainder 1. It works. This theorem powers and public key cryptography systems. All this math is fascinating, but it becomes truly powerful when we can make a machine do the work for us. That is where programming comes in. A program is just a sequence of instructions written in a language the computer can understand. We will use Python, a language famous for its clear and friendly syntax. The first step in any program is usually working with data, and we store data in variables. A variable is like a labeled box where you can put a piece of information. For example, age equals 30 creates a variable named age and puts the integer value 30 inside it. Python automatically figures out the data type int for integers, a float for numbers with decimals, a str for text, strings. Once we have variables, we can perform operations on them using operators, plus for addition, minus for subtraction, times for multiplication, divide for division. Python also has double star for exponents, so 2 double star 3 is 8 and percent for the modulo operation, which gives you the remainder of a division, so 17% 5 is 2. When you combine these in one expression, Python follows the order of operations, PEMDAS, parentheses, exponents, multiplication and division from left to right, addition and subtraction from left to right. This ensures that 2 plus 3 times 4 is calculated as 14, not 20. As programs get more complex, we need a way to organize our code. We do this using functions. A function is a named, reusable block of code that performs a specific task. You define a function once, and then you can call it whenever you need it. This makes code cleaner and easier to debug. For instance, we can create a function to add two numbers, def add numbers a, b. Inside the function, we specify what it should do, like result equals a plus b. And then we can tell it to give back the answer using the return keyword, return result. Later in our code, we can simply write some value, marge add numbers 5, 10, and the sum value variable will hold the number 15. Good function design is key to good programming. A well-designed function should do one thing and do it well. It should have a clear descriptive name that tells you its purpose. By creating small focus functions, you can build complex programs by combining these simple blocks like building with Legos. This approach makes your code easier to read, test, and fix. To bring everything together, imagine creating a one-page revision sheet. On one side, list the math concepts, equality versus equivalence, number sets, logic operators, number theory rules. On the other side, write the corresponding Python code, double equals operator, $psi, for checking equality, numeric type, inti, numeric type, float, logical operator, and, logical operator, or, logical operator, not, percent operator for modulo, percent. This sheet becomes your bridge, visually connecting the timeless principles of mathematics to the practical art of programming. Let's get